Okay, good evening. Today we are going to look at convolutional neural networks. So we have started on the journey of looking at neural network architecture. Before now, what we have really been doing mostly has we've been looking at different ways of training models, different training approaches, different training algorithms, different model architectures. Um, we've mostly been looking at classical algorithms with linear regression, logistic regression, classification. Then we looked at the different types of tree, decision tree, random forest, XGBoost, support vector machines, SVMs. Then we looked at the other supervised, unsupervised, the K-means, K-nearest neighbors, K-means, clustering, PCA, and so on and so forth, right? So many different approaches from classical machine learning. Then we visited neural networks and we talked about the different aspects of neural networks, the architecture, basic foundations of architecture. We looked at the whole single layer perceptron or neuron. Looked at two layers, hidden layer, output layer, input layer. Looked at multiple layers. And then we understood that neural networks are units of computation, basically a single unit of logistic regression. And then we expanded that. Then we looked at training, we looked at optimization, we looked at different kinds of cost functions, criteria. We looked at bias variance. So we looked at a lot of things, right? Interestingly, all of those things, including regularization and the loss landscape and all of that, those are just, as far as neural networks are concerned, those are just kind of laying foundation for how to train models. But when you come to neural network, deep learning, deep neural network, um, we begin to talk about the different types of architecture. And we had already kind of touched on basic architecture when we mentioned the fully connected layer. And then when we looked at a multi-layer perceptron, which is essentially a neural network that has multiple layers, 2, 3 layers, instead of just a single layer. We had already started looking at architecture, but those were basic architectures, linear layer. So now we'll start looking at other types of architecture. We will look at the convolutional neural network, which is what we'll talk about today. Then we will look at recurrent neural networks. Okay. Convolutional neural networks, recurrent neural networks, or sequence models. Then we'll look at the more modern deep learning that are like the foundation for the large language models that we are hearing today, the attention mechanisms, transformers, and then we'll look at generative models. So when you look at this, the last 4 or 5 topics that we'll be handling is more about different structures of how you organize the neurons in a deep neural network to get better efficiency for specific tasks. We are no more talking about training dynamics because all of what we talked about in training dynamics apply the same way to all of these, right? Things we talked about like activation functions, even though activation functions begin to have a little bit more impact in deep neural networks, but still it's not going to have as much impact as the learning rate that you choose or the optimizer that you choose or the data that you are using for training. However, when we want to talk about specific kinds of tasks that you want neural networks to do, the tasks that begin to be more impressive, the wow factor, convolutional neural networks begin at the beginning of it, right? Yes, we could say if you did a standard fully connected deep neural network, it would predict price of housing. Okay, that's nice, but there's not much wow factor there. But when you start talking about neural networks that can look into images and tell you what is inside those images, that is where CNN comes to play. CNN was specifically and specially designed for image recognition. So we're going to look at the architecture, what is the basis for it, and we'll talk about some of the terminology like filters, um, kernels, feature maps, and so on. We'll talk about convolution. What is even a convolution, which is actually a mathematical operation. But of course, everything here is all about maths. It's all about the application of maths. So we'll talk about that, convolution, filters, pooling layers. We'll talk about the modern CNNs, ResNet, residual network, efficient net, and then we'll talk a little bit about transfer learning. Transfer learning is when you take a model that has already been fully trained and you adapt it a little bit. You just maybe add a few weights at the end and retrain it with new data so that it can um, be used for a similar function, right? Um, Transfer learning helps you to minimize the amount of compute that you need to do to train a model because you're not really training it from scratch. So let's get into it. So what is a convolutional neural network? Whenever you hear CNN in machine learning, that's what we're talking about. It's not the news channel or anything else. It means convolutional neural network. And it's a special type of model, of neural network model that is designed specifically to extract hierarchical features from grid-like data that is two-dimensional in nature, right? Such as images. In other words, data that is spatial. In this case, the spelling of spatial is not what you think, but it has to do with space, two-dimensional space, right? So that kind of data, that is what spatial data, right? That kind of information. So it's grid-like, it's two-dimensional. It has X and Y axis. It has rows and columns, right? So examples of that are images, but it's not just images. There are other kinds of data that you would use, right? But images come to mind quickly, and you'll find that images are the one application that is predominantly being used for CNNs. So why CNNs are so good with images is because of what we call convolution, which we'll talk about shortly. Convolutional layers. So there are some aspects of the architecture that become very key, right? So we have what we call the convolutional layers, we have what we call the pooling layers, and then we have the fully connected layers, which are used to do the final representation. So when you look at all of that, the CNNs kind of mimic the human visual cortex. So this is now a second situation or example where we are using human anatomy as an inspiration for designing a neural network, right? Or designing an AI or machine learning model, right? We talked about how an artificial neuron is kind of modeled after the human brain, the neuron in the human brain. Now we are looking at is a convolutional neural network, a whole stack that is kind of modeled after the human eye. The visual cortex is the part of the human brain that actually addresses or handles vision, the stimulus from the human eye, the stimulus from the two eyes. That's the visual cortex. So CNNs were kind of designed similar to that and to perform tasks. So the kind of task that your CNN would perform would be tasks like image classification, right? Object detection, and medical imaging analysis. Those are just a few examples, but you see that the common denominator in all of this is image, right? The fact that we are doing all of this on images, it means that CNNs are kind of optimized for images. So we'll delve into a bit more and how it works, how it is so successful when it comes to images. So before we go into that, the first thing we'll ask is, what is the difference between a convolutional neural network and a fully connected, network? We already talked about a fully connected layer. So you can see that in a fully connected layer, like we said before, all of the inputs are connected to all of the outputs. In other words, each neuron in a previous layer is connected to every other neuron in the next layer. And you can see in this case, this neuron A is connected to all of these neurons or inputs in the previous layer, 1, 2, 3, 4, 5, 6, 7, 8, 9. Same thing with B, right? Same thing with C, and same thing with D. But in a convolutional neural network, you don't have such. There is actually a structure of how the neurons in the next layer are connected to the neurons in the previous layer. They are not connected to all of them, but they're connected to the ones that kind of are in the same space, if you may look at it that way, right? So this will not really make sense because we are looking at a flat layout of the input neurons and a flat layout of the output neurons here. It makes most sense when you go into a two-dimensional space, right? And look at it, then you can, it makes most sense of how you derive the output, by looking at the inputs, because it's designed for that spatial consistency, right? I will look at some of that. So the convolutional neural network doesn't have as many weights. Of course, what this means is that it doesn't have as many weights as the fully connected. So it is more efficient to do the computations, right? And that's why it is so powerful. The fact that it can achieve a lot without having to have as many parameters, right? For the same number of inputs and outputs. It has far less parameters than a fully connected neural network. And so it's able to achieve more. So an example is, let's take images, because all of this is about images. When you take an image is basically a two-dimensional matrix of numbers, right? Those numbers represent pixels. A pixel is effectively a single square that is so tiny on your display or on your screen or in an image that you will not see that single square by itself. When we look at pictures, what we are seeing is an aggregate, an array, or a matrix, a two-dimensional matrix of pixels. That's what we're actually seeing. And each pixel is so tiny, you cannot see it individually, but you see all of them coming together. So the pixel has a value. And the value of the pixel depends on um, two main factors, right? One is the color of that pixel, and two is the transparency. Transparency is whether you can see things behind it or not, okay? Now, the color of a pixel is made up of three parts. The three parts are the R, the G, and the B. The R is the amount of red in that color. The G is the amount of green in that color, and the B is the amount of blue in that color. For those of us who did a bit of physics and maybe a bit of fine arts, you would have learned that you can get any color by mixing three colors that are normally called the primary colors. Okay, so in fine arts, the three primary colors are yellow, red, and blue. because that in fine art is subtractive. Effectively, you are mixing pigments. But in physics, the three primary colors are green, red, and blue. You are not mixing pigments, you are mixing light, colored light. Colored light, when you're mixing it, is additive. But when you're mixing colored pigment, it is subtractive. Because a pigment is actually a reflection of light, from the surface of that pigment. And the pigment absorbs the wavelengths that it doesn't want to reflect. It only reflects the wavelengths that match the color that it wants to show to you. So that's a whole other science, which I will not go into. But when you're talking about light, right? If you do some experiments, you can take light of, those three colors of light, red, green, and blue, and you can mix them in different proportions. You can get any color out of it. So that means every color perceptible by the human eye can be expressed as a mixture of different proportions of red, green, and blue. For those of you who are front-end developers, who have done some coding before, and maybe you've done front-end, those three colors are normally specified as RGB or as a hexadecimal number that is made up of 6 digits. The 6 digits, two of them represent the amount of red, the first two. The second two represent the amount of green, and the last two represent the amount of blue. And then these days, you now have a fourth set of two numbers that represent the transparency or alpha. So those four numbers can be used to characterize a pixel, basically the color and the transparency. Of course, the last aspect of a pixel is where is it positioned in a two-dimensional grid, right? Where is its X position and Y position. But when you're looking at a neural network, it doesn't really matter because what you are doing in a neural network, the input is you are taking that two-dimensional grid of colors and you flatten it into a single vector. And when you flatten into that single vector from top to bottom, right, left to right, left to right, left to right, you convert it into a single vector. That becomes the input that you will put in. So if you have a color image that the size is 224 pixels height or width, we typically do width before height when we are looking at dimensions of images. So the 224 pixels wide by 224 pixels high, then because it is a color image, it is going to have three components, the red component, the green, and the blue. So the total number of inputs, each of those represent an input that you are taking into the neural network. If it is a black and white image, then this will not be three, this will be just one, because for black and white, you only need a single number that represents how bright or how dark that particular pixel is. So a color image of size 224 by 224 by 3, 3 because there are three, the RGB, right? So those RGB will correspond to three inputs that will go into the neuron. And then for each of those pixels, there are 224 on the y-axis and 224 on the x-axis. So you have to multiply and multiply by 3. That gives you a total of 150,528 inputs. That's the number of inputs that you would have to sense or design your neural network for, right? So if you take this 150,528 inputs, that will be your number of inputs. Then you will now make the first layer of your neural network to have maybe 1,000 neurons. Okay. So if you have that, let's just assume, because this is even, it should even be as much as the inputs so that you don't lose information. But then that will not be manageable. So, but just assume that we take 1,000 neurons in the first layer. So that the number of weights would now be 1,000 times this 150,528. That's 150 million weights for just a single layer, right? That is the problem with a fully connected network. If you're using a fully connected network, the parameter count will explode, and the ability of your model or the computational capability of the GPU, CPUs to actually compute and solve your model, train your model, would be it will be very difficult. So in practical terms, using fully connected networks for image task is not practicable, right? It will be very slow to train such a model, and you need a massive amount of data, because the amount of data that you have needs to correlate with the number of parameters you have, or the number of features, right? Otherwise, you will end up overfitting. The network will end up overfitting because it has too many parameters. It is too complex, right? So that is the problem with using a fully connected network for images or any other flat two-dimensional grid-like data structure. So the second reason is that fully connected layers will treat every pixel as if it is independent, as if they are separate from each other, right? It will not know the relationship between pixels that are close together or pixels that are far apart. It will not be able to understand the patterns, right, that may repeat across the image, because the inputs are just coming in as separate inputs. So just try to visualize these numbers here, 1 to 9, and just imagine that um, there were 150 million of these, right? And you take a picture of your face, and then you deconstruct it into pixels, and each of these represented one pixel. How would you even be able to kind of characterize, okay, your nose? Which are the inputs that map to the pixels that make up your nose? It is not even easy for a human being to think about it or to, understand or conceive it. Same way, it's going to be difficult for your model to also pick it up. That's what we are saying. There is no concept of nearbyness, right? Nearby pixels, because when you look at this fully connected, the weights here, are random initially. There's no there's no correlation between weights of inputs that are close together and weights of inputs that are far apart. It's difficult. You cannot just get it from looking at it this way, right? So the fully connected networks are really good for flat type of data, or data where the relationship, there's no spatial relationship between the different inputs, right? Rather, the relationship is kind of behavioral or functional, okay? But the other thing with fully connected networks is if you have a pattern at the top of the page or the top of the image and a similar pattern at the bottom, they will be seen as two different patterns. So if you have a picture of a cat at the top left of the image, right, and the picture of the same cat at the bottom right, the fully connected network will see them as two different things. You do not conceive them or think of them as being similar or the same thing. So those are the challenges with using fully connected network. I think at the beginning, in the early days, people actually tried using fully connected networks for image recognition. They found that it was not working out. So researchers, again, started looking for better ways. Okay. So now, why do we need something better? And that was a question, right? We need a model that can look at small regions at a time, okay? Because of the size of images, because of the complexity of images, because of the number of pixels. We don't want to look at everything at once. The main reason why you don't want to look at everything at once is patterns do repeat in images, right? So, and those patterns that repeat should be recognized as the same thing, right? Or similar things. They shouldn't be seen as totally different, because for a fully connected neural network, the position input at position A is different from input at the same input at position S, or input at position 10 is different from the same input at position 15 or 20 or 120, right? But in a convolutional neural network or in an image, a cat at the top left is the same as the same cat at the top right or in the middle of the picture. So we need a model that can zoom in to smaller regions, right? And use that same pattern detector to detect every part of the image and then to build understanding of that image step by step. So that is what led to the should I say invention or discovery or development of a new approach, which we call the CNN, the convolutional neural network. And it started off by a basic foundational mathematical operation called a convolution. And we're going to talk about that. But if you look at an input image, this is just kind of an example of it. The way convolutional neural networks now work is you take a small patch, which is this square here, which you can call it a kernel or a filter, right? You take it and you scan through this and you pull out features as you scan through it. And this particular filter will identify certain types of features. You take another one, which is the one behind it here, and you scan the same image again. And it also will identify a different, set or type of features. Okay. And so on and so forth. So you have a lot of them here. Maybe here is up to 8. So you take each of these 8 and scan the same image. And the interesting thing is that when you use this kernel, each of them that scan generates a new output, right? It generates a new output that is basically the foundation of the next layer. And so if you have 8 of these filters, then the output here there will also be 8 of these outputs corresponding to 8 of these filters. So you now see that you have 8 outputs here, even though you only had one input image, right? But you now have 8 outputs. And then you now have what we call a pooling layer. So what pooling does is it takes this output and it makes it smaller so that the next layer will have less work to do. But more importantly, we would have crystallized more of the important features out. So just like in a regular neural network, fully connected layer where each layer did some feature engineering, in convolutional neural networks, the same thing. Each of these filters is doing some kind of feature engineering and is creating new sets of features in the next convolutional layer, right? That new set of features identifies a new um, set of characteristics, right, from the same input image. And then the pooling is able to kind of average things out. So you begin to see average stuff. We'll talk more about that. But the interesting thing is that even though we have already said a fully connected layer is not very good for image recognition, but at the tail end, you still need what we call a feed-forward layer, which is effectively just a 2 or 3 layer fully connected layer, right? That's called a feed-forward layer or a feed-forward network. And that is then what is used to represent the meaning. So effectively, what each layer in a CNN is doing is feature engineering, like we talked about, in a continuous stack. But at the end of the day, you now have a much more refined feature engineered or refined set of features that will now go into the feed-forward layer to form from where the representation of the knowledge comes up. So all I have just said is what you now have on this slide. The fully connected networks are not good for images. The advantages of CNNs over fully connected networks for image tasks is the local connectivity, number one, because the neurons in the CNN only connect to a small local region of the input, what we call a receptive field, right? So it's not trying to scan all the pixels at once. or try to calculate output by taking in input from all the pixels at once. Rather, it is taking the pixels in small blocks, right? Which those small blocks is what we call a kernel, right? That's a kernel size, or that's a patch. Okay. So what that does, and it's two-dimensional by design, it's designed to be two-dimensional because we know that images are two-dimensional. Actually, it's three-dimensional because the third dimension is brought in by multiple kernels, right? That stack to form a volume, which we call a filter. So technically, you can see a kernel as I always see a kernel as a single flat two-dimensional patch, while a filter is a three-dimensional version of a kernel. In other words, lots of kernels that are stacked in a particular volume. We'll look at that. So that's the first advantage because it is looking, you know, in small, it's looking at small um, patches of the full image, right? So it's able to understand patterns. So if it finds a pattern at the top left and finds the same pattern at the top right, it will recognize that the same thing because it is now what is now space invariant, which is what other, that's the next thing we'll talk about. Then the second benefit of the CNN is weight sharing because you're effectively using the same two-dimensional patch. That patch is made up of parameters. So the parameters are in that patch. You're using that same set of parameters and moving across. Unlike a fully connected layer where the parameters are fixed, right? Between the next layer and the previous layer, you have a connection. Each neuron is connected to all of the other inputs or all of the other neurons, and the weight or the parameter is fixed between those two neurons. They don't shift. But in a convolutional neural network, the that patch, that kernel, is what makes up the parameter and is what connects the output to the input, right? So it becomes shared weights as you are using it across different parts of the image. You can see that you're using the same weight across different inputs and you are transferring the results of that calculation to different output neurons in the next layer. So it is shared weights because you are using the same convolution kernel. So we'll talk about kernel. The kernel is just a single, you know, shape, either a square, right, or a um, a volume, right, that effectively embodies or carries the weights, okay? And it is the weights in that kernel that form the parameter, but that same kernel is applied across the entire image. So what this does is that it significantly reduces the total number of parameters, mainly because you are no more having dedicated parameters or weights that are connecting each input or each neuron in the input to the neuron in the output. You now have weight that moves, that are shared, between different sections of the image. So that reduces it. So imagine that same 224 by 224 by 1000 that we talked about before. Sorry, 224 by 224 by 3, okay? If we had just a single 3 by 3 kernel, right? A single 3 by 3 kernel will then have, you would use a weight of that single 3 by 3 kernel for all the 224 pixels, all the 224 by 224 pixels, right? So you have reduced that complexity from 224 times 224 to just 3. That is a huge reduction in the amount of parameters you need for you to map an input, to the output, that is to the next layer. So it significantly reduces the total number of parameters. Therefore, the training is more efficient and it reduces overfitting compared to the dense, fully connected layers that we talked about. Then there is a translation invariance or space invariance. Because of shared weights and pooling, right, and the kernel moving around, okay, the convolutional neural networks can recognize features regardless of their exact position in the image because you're effectively moving the weights from one part of the image to the other. So the weights that have learned to recognize a particular pattern will recognize it irrespective of where on that image it is because it is moving around. Okay. And because it is moving around, if the pattern is at the top left, it will recognize it. If the pattern is in the middle, it will recognize it. If the pattern is at bottom right, it will still recognize it. Okay. Because it's been trained just to recognize just that pattern. So you can now look at the kernel or filter, which is the part of a convolutional neural network that is actually learning, it's actually getting trained. You can see it as, um, you know, a specific pattern recognizer that has been trained to recognize just one specific pattern. And wherever it sees that pattern on the image, it will recognize it, right? So, that means they're also very robust to small shifts, rotations, or distortions. Then there is one other aspect which we need to mention, the hierarchical feature learning. So remember what we said, each layer in a deep neural network is learning features. Now, when you apply that same principle with convolutional neural networks, you find that each layer learns low-level features, early layers rather, learn low-level features at the beginning. So the first two, three, four layers in the CNN will learn the edges, the colors, the lines and so on. But as it goes deeper, the deeper layers begin to combine these features because when it learns the features, right, what it does is effectively engineer those features into the next layer, what it has identified. So the next layer is going to contain a new representation that contains more complex features or more refined features than what is in earlier layers. And so it just keeps going on and building up. So when you get to the deeper layers of the convolutional neural network, then the deeper layers begin to identify and recognize more complex structures. They begin to recognize shapes, circles, squares, rather than just edges and colors, right? Circles, squares, and irregular shapes, right? And even objects. And then deeper down, it begins to recognize more complex objects like an eye, an ear, a mouth, depending on what it was trained for, an elbow, and things like that. And as it goes even deeper and deeper, it begins to composite all of those more complex, things it has recognized in the image to form larger objects, people, animals, and so on. That is what we call hierarchical feature learning. Hierarchical feature learning basically means the earlier layers in a deep neural network learn simpler low-level features. As the signal progresses deeper into the neural network, right? The deeper layers begin to learn more complex structures by combining the simpler features that the earlier layers are learning. So it is a progressive um, improvement or increase in the capability, of each layer to identify more complex features in the images, right? Then the last bit where CNNs are really good is overfitting is much reduced simply because of reducing parameter count. Remember, overfitting happens when the number of parameters in your model is far more than the amount of data that you have. The number of parameters can depend on the number of features that you have or columns in the data, but it could also depend on the number of layers for something like a neural network, or the number of connections, like in the case of a fully connected layer, right, or fully connected network. So what CNNs do is, first of all, you are reducing the number of parameters by using kernels instead of just doing a direct dedicated weight connection between each neuron in each layer and the next one, right? But you also do other things like pooling, right? The pooling is essentially averaging, and you do that, after you have done the feature engineering, which is effectively not the feature engineering. When the layers, after each layer, you do pooling. The essence of the pooling is add to average and kind of extract um, a smoother, more general, um, you know, expression, if I may put it that way, of that feature. So by the time you combine the shared weights, which acts as a form of regularization, and also the shared weights also reduce the number of parameters, which also acts as a form of regularization. But at the end of the day, it's effectively less parameters means less overfitting. Then the spatial pooling, which is the averaging, the CNNs become much better at generalizing. So when you have trained your model, it becomes much better, for use to other things, so other applications, right? And they're able to predict unseen data much better, because um, of less parameter count, they overfit less. So some of the ideas behind the CNN, the local receptive field. So when we say receptive field, what we mean is that if you look at an image, right, the convolutional neural network is not looking at the whole image. It's just looking at a piece of it. I'm going to show this shortly um, with a few uh, you know animations and graphics, right? So if you are having difficulty following this, don't worry. I'll soon clarify with actual examples. But when we say receptive field is saying if you have an image, so let's assume you have an image, um, something like this, right? Let's assume this square contains an image. So I have an image, but I am only going to scan this image. I'm not taking the entire image and passing it as my input. I would rather scan it, you know, um, you know. So to scan it, I'll take a small, this small kernel, right, which represents a sub piece of that image. I'll take it and I'll scan it. So you think of it as if you are scanning, just the way your eyeballs will scan, even though the human eyeball scan in a random manner. It is not in the systematic approach that we use with CNNs. But with CNNs, I'll take this, let me make a transparent one so that we will get it much better. So let's assume you have an image here, and this is the original image. Okay, that's this big one. Then you have a smaller image, this is not an image, this is just um the kernel, which is the subsection, the sub uh area of the image that you want to scan. So you're going to look at just a small piece of this image at a time. And then you keep scanning it this way, effectively scanning it from right to left. When you get to the end, it will now move to the next line, the next pixel row, and it will scan. And it normally goes down one pixel row at a time, and it will scan. As it is scanning from right to left, it is picking up features in this image, right? So this is like how scanners even work. Okay. So you can see that this kernel that I'm using to scan, this small kernel that I'm using to scan the larger image is not seeing the whole image at a time, at a go, right? That is what we call receptive field. A receptive field is basically the area of the kernel, the area of the image that this kernel is able to see at a given point in time. That's the receptive field. It's not seeing the entire image at the time, but rather a small subset of it or subsection of it, right? So each neuron, well, I wouldn't technically say each neuron, but rather each group of neurons, each kernel, right? Each kernel is going to look at a small window, 3 by 3 or 5 by 5, section, as you can see here, 3 by 3 or 5 by 5 pixels at a time, right? And that's how images work, because the smaller this receptive field, the more capable of this kernel to be able to identify the parts of the image that matter. The edges, the corners, textures, right? The edges is where it will start first to identify where there's an edge. An edge is kind of the difference between one color and the next, right? When you have a color transition in a pixel, that marks an edge. And these kernels are designed, we'll look at the principle of convolution, which is the mathematical principle algorithm that's used, to create it. But that mathematical principle algorithm ensures that it is able to detect where there's a color change or a color shift. That's what we call edges. An edge is basically where the color changes. So for example, if you look at this rectangle I just drew, at this square, you see that here the color is you know, pinkish. Here the color is white. The edge is a point where the color has changed. This is a simple thing to understand. So you have another edge here where the color has changed. And then the corner is where two edges meet, right? So over time, if I were to scan, if I just look at this is a very good indication. If I'm scanning an edge, you will see that the kernel has a different color on this side of the edge, and on this other side has a different color, right? Because it is kind of picking values from the substrate, that is the image itself, and it is calculating, its differences. That's a convolution operation, right? So when it's calculating difference or the sum, whichever one you want, you see that the color here, out here, the color is the same. In here, the color is the same, right? Even though it's different, like it's uniform. The color in here is uniform. The color out here is uniform. But on the edge, you can see that some parts of this kernel have a different color from the other one. So this kernel is designed to identify such things, and it will identify that and propagate it to the next layer. And this everything at this point where it has identified this change or shift in color will be identified as edge, right? So that is how that works. Edges, corners, textures. Okay, so that's what we mean by a local receptive field. Then the weight sharing is, like we said, the same filter is being used to scan every portion of this image. So because it's being used to scan every portion of this image, okay, it is kind of shared weight. The parameters in this kernel will be trained to be able to recognize, it will be more generalized because it is looking at multiple things. So the noise will go away. It's going to actually learn how to identify specific things. The same filter is used at the top of the image. This same filter will be used in the middle of the image, and the same filter will be used at the bottom of the image as well when it is scanning. So it doesn't matter where a vertical edge exists. If the vertical edge is here, up here, down here, right? Or on this side, it will still recognize it as an edge. So a particular kernel that ends up being trained to identify edges will identify edges everywhere. This is a key um, premise and principle behind the convolutional neural networks. So the benefit is that you have fewer parameters, again, because you're using this same kernel, this same weight, this small square, small blue square, basically are the parameters. So you can see that since I'm using a smaller one to scan all of this, the amount of parameters is much less than if I were to use maybe a bigger one, that I want to use the one that fits in directly with the size of the image like this. You see that there'll be more parameters here, right? And that is not as efficient. So because the parameters are fewer, the model is also going to learn faster because the speed of calculation, I'm sure all of you have done a bit of training. You've gotten that experience already, that larger models that have more parameters take longer to learn. Of course, because the computation is more, right? So smaller kernels, smaller models, smaller kernels, smaller parameters, less parameters will get trained faster. Better generalization again, because it is scanning all of them, it is getting information from all of them. It's able to discard the noise and basically boost the signal. So it generalizes better. So that's weight sharing. Then spatial hierarchy, I mentioned that already, where you are saying that the first layer learns, you know, low-level features like edges and lines. The middle layers begin to learn more complex. Corners now become where edges meet, right? Textures become multiple lines. And then deeper layers, we have shapes. A shape could be like four corners or three or two or three corners coming together, right? If you have two corners coming together, that's a square. And if you have more, you start having shapes, and the shapes start coming together to form objects. And this is how the human vision actually works. So in a way, you can see that when we say it was modeled after the human visual cortex, it is true, right? There is a translation invariance, like I said, which is when if if something in the image were to be shifted from one part of the image, maybe from top right to another part of the image, maybe bottom right or bottom left, it will still be recognized. It will still be recognized. The CNN will still recognize it because of the fact that it's a small kernel that is checking those different parts of the image. Okay. So the same filters will scan everywhere, kernel and filter, same thing. It's just that a filter is a three-dimensional version of a kernel, right? Even though people sometimes call filters kernels and kernels filters. Pooling reduces sensitivity to the exact position because the pooling is averaging, right? So it's averaging from multiple positions. It takes the average. So irrespective of which, it's kind of um, it's a generalized version of it. So that's why convolutional neural networks work very well for object detection, for face recognition, for medical imaging. Anything that has to do with imaging, it becomes very good at it. So I think in the process of this explanation, which I have taken some time to delve in, I have mentioned a bunch of terminology. We'll still go into a bit more detail on some of them. But I've already talked about convolution. Convolution is a mathematical operation that is a underlying, you know, algorithm behind this scanning we're talking about. When you take a filter or a kernel and you you point it at a particular part of the image and you extract features from it. That is done through convolution. Filters, already said it, the kernel, that's the thing that moves around, right? A three-dimensional one is what we call a filter. I'll show you that. Feature map. So a feature map is what comes out as the output from the scanning. Essentially, a new set of features that have been generated, by scanning that image with the filter. Stride is essentially when you are scanning, how many steps do you take, as you're moving from right to left or top to bottom. The stride is how many steps you take. If you take one step at a time, that means stride one. If you take two steps at a time, that's stride two. Padding is additional, um, should I call it fake, pixels that you put around the image. That there's a reason why you do padding. It's not part of the original image, but you need it to maintain maybe the same size, the size consistency, or for you to be able to have a whole number, to not have fractional not have fractions when you are scaling down images and so on, right? So it's kind of fake pixels. Typically, it is either empty, zero value bits or bytes. Remember I said that each pixel is represented by a number, and that number is a combination of the three numbers that make up the RGB, right? So um, we pad it. We can pad the image with fake pixels around the edges, top edge, bottom edge, left edge, right edge, right? In order for the convolution operation, the scanning operation to give us whole numbers instead of fractional components. That's what padding is. Then we already know what activation function is, which is when you have scanned and you've gotten the output from one layer, you can apply activation function to it. So unlike the fully connected layers where you do a product sum, right? A sum of products of weight and the input or input activations. For the convolutional neural network, you are not doing a product sum. You are just, it's still a product sum anyway. It's still a product sum, but yeah, the product, the weights are now inside the kernel, right? That you are scanning through, and then you calculate it. So you see the dot product like we have been doing before, and we are going to see how that works. Then we talk about pooling. So pooling is averaging. Well, there is max pooling where you take the maximum, but it's just a way of combining and reducing the footprint of the image. We'll look at that in more detail. Stacking convolutional layers. So when you take multiple layers, convolutional layers, and you stack them. That is the basis of that hierarchical representation, because each layer will essentially do feature engineering for the next layer. The next layer will take it and do feature engineering and so on. Receptive field is the area in a particular given image that your kernel is looking at a given time. Weight sharing, we already talked about that. Spatial hierarchy of features, I talked about that. Flattening is what you do with pooling. And then fully connected layers, we know that. Then the output layer, which is the softmax or sigmoid. So now let's look at this. This diagram really helps to visualize again what we're talking about. You have 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have this larger image that is broken into smaller patches. So 9 patches, right? These 9 patches are not 9 separate images. They are, okay, well, I think the way you can look at this, there are many ways to look at this, right? But I prefer to look at it as a single image, right? That has multiple pixels. So you can see that if you were to just count, let's assume you could see the pixels. Here you have 1, 2, 3, 4, 5, pixels in this one direction, and in this other direction you have 1, 2, 3, 4, 5. So each of these smaller cubes is 25 pixels area, and then of course the depth. But let's forget the depth for now. So you have 25 pixels, and 25 pixels. You can also do it across all three. So this is 15 by 15, right? This entire section is going to be 15, right? And then the other section is also 15. So this is 15, okay? And this is 15. So if you do that product, that means you have a total of 225 pixels here. Now, you take a kernel. So what's a kernel? This is the kernel, this little thing here. And it has a receptive field. So the receptive field is which part of this particular, we have taken this 15 by 15 and we slashed it. We split it into 3 in each direction, 3 in the X or X direction and 3 in the Y direction, whichever, right? So this kernel is going to look at one block at a time, and it's going to pull the features, it's going to scan the features here. Each of these is a single scan, and then it's going to extract it and do the convolution operation, and then it's going to send an output to this. So this output here now corresponds to this block, and that's what it is. So if that continues, okay, this thing will now move. And I have an animation that will show. This thing will now move a little bit to this direction. And if it moves in that direction, right, it will move to this direction. And this time around, maybe it will effectively take a scan of this one. And then when it takes a scan of this one, it will map it to this position in the middle, right? Later on, it can take a scan of another one. Maybe it takes a scan of this one and it will map it here. So of course, it's not doing it randomly. It's actually doing it sequentially. It's just that we are seeing in the middle, but it's always sequential, starting from the top left and going rightwards. And then it goes down and goes rightwards and goes down, goes rightwards. And at the end of the day, it's going to scan these 9 blocks and it's going to map them into the corresponding 9 points here. So this is the first layer. This is the kernel, which has the actual parameter, and this is the next layer. So this next layer now has new features, right? That comes from this single kernel. Now, this is a single kernel. If you stack the kernels, then the you now have filter. So each kernel in the filter is going to generate this same this same um, output, right? Which is going to be stacked as well. And then you end up having a stacked output. So the kernel moves in horizontal and vertical directions, right? As it is moving, it is scanning a subsection of the image. It is applying the convolution operation on that subsection. And the output of that convolution operation goes into the next layer. That's it. That output, that's a convolutional result. You can see that the input is this, the kernel is this, right? And then the output is this. That is a summary of how the CNN works. This is another way of looking at it, right? In this one now, for this one, we're looking at just a single layer. So this is just a single layer. Convolution from one layer, the input layer, to the next layer, the output layer, right? And now here you have multiple layers. So you have a layer, you have another layer here that is made up of 2 convolutions and a max spool. Then you have another third layer here that is made up of 4 convolutions and a max spool, right? Then you have another layer here that's made up of 5 convolutions and a max spool. And it just keeps going like that. So for each time you do a convolution, this is a bit difficult to understand or explain, but it's another way of looking at it. I have a better one later on which will clarify. But for each of these, you see that you are generating features. Each layer, a previous layer is generating new features for the next layer. Okay, so the foundation of all of this is the convolution, right? What is the convolution? A convolution, like I said, is a foundational, fundamental mathematical operation. Okay. And you will really only hear of convolution in the convolutional neural network. That's why it's called a convolutional neural network. It's a mathematical operation that is used to extract the spatial features like the edges, textures, and shapes from the data. And it involves sliding a small filter or kernel across an input, such as the image, to calculate a new feature map. So when you are doing that sliding, right, you are for each patch that you tick, you create a new neuron or a new output, if you may put it that way, a new output, in the next layer, and you keep doing that. So that filter will calculate a new feature map which forms the output. And that feature map is created by multiplying the filter values with the input pixels and then summing them. So it is still a product sum, just like what we were doing in a normal, um, you know, um, multi, fully connected layer rather, in a fully connected layer. So it's a multiplication and then a sum, and I'm going to explain that shortly. right? But what that does is that it allows the model to detect local patterns regardless of their position. So now let's go back and let's look at this one again, okay? And now let's assume that we are looking at it from the standpoint of here. So you now see there are three things. Let's assume this one at the back is the image, okay? And remember I said that images are represented by pixels. So let's assume, well, it's not an assumption, that's the reality. The image is actually a two-dimensional grid of numbers. And the number in each cell represents a pixel value, okay? Now let's assume that this image is a monochrome image. It doesn't have colors, it's just monochrome or grayscale. So it means it can only have one value in here, not three values, right? The pixel, there's only one pixel value. If it is color, there'll be three pixel values or maybe four, depending. So these numbers represent the intensity, how black or how light, the pixel there is. So let's assume 9 means a very bright pixel, while 1 means, or 0 means a very dark pixel. So you have these numbers that basically come from the pixel that make up that image. Okay, this is a very small patch of the image. In a real image, the pixels are so tiny, you'll not see them. But let's just do this. And that's really what's happening. Now, here, this second layer here is the filter or kernel, right? So this is just one of the dimensions in a multi-dimensional filter. And you can see it also has numbers in it. These numbers represent the parameter, the weights of this particular filter, what it has learned over the training, so far, right? So these numbers, think of it like when we're talking about the weights in a normal fully connected layer, that you multiply the weight by the input. These numbers represent the weight, while these numbers represent the signal, which is the pixel value. Okay, so the output is I take this filter that has these weights and I apply it to each section of this image. So here, this part of this image that is blue is the section that this filter is looking at any point at the first, instance, right? And the output is now a product, a sum product. If you look at it, this output 16 is the convolution operation of this filter on this section of the image. And it's very simple mathematics. You can even see it here, right? 9 times 0 plus 4 times 2 plus 1 times 1 plus 1 times 4 plus 1 times 1 plus 1 times 0 plus 1 times 1 plus 2 times 0 plus 1 times 1. That is what is happening here. That's basically what I said. 9 times 0 plus 4 times 2 plus 1 times 4, right? So each corresponding pixel, right, is multiplied by that same cell in the filter that is mapped to that pixel. And when you multiply it, right, 1 times 1, 1 times 4, 1 times 1, 1 times 0, 1 times 1, 2 times 0, 1 times 1. You now sum. So that's why it is a sum product. You do the product of the individual elements and then you do the sum. You can think of it like it's also almost a dot product, except that it's easier to think of convolution as element-wise product, sum product, but it's the same thing. And then when you add it up, the total is 16. And 16, that total is the value in this output array. This is simply what convolution is. So the question is, how do I get the value of this next cell? I will shift this same filter by 1. So we will now be looking at this. We'll now be looking at this, right, to calculate the second one. So this, when you look at this, it will now map, and the value from that multiplication, that sum product, right, is going to be put in here. And then the third one, we will now look at this. Remember, the shape, the dimension has to match the filter. And that is what will go into this array. Okay. And then the fourth one would be this one. We'll go to the next row because we have gotten to the end of the first row. We now start the second row and we'll map that one here, right? And we'll just keep going that way. The same sum product operation and the values from each of them will appear here until you fill up this. And this becomes the new layer. That is the activation or output of the new layer. In fact, you can call it the pixels of the new layer, but it's not really pixels now because the neural network has started doing some work on it. Essentially, this is now a slightly feature engineered version, right? Based on the properties of this kernel, right? This kernel now has properties, and the properties are characterized by the weight, right? It is the weight, these numbers in this kernel, that determine how the numbers come out here. So if you now have another kernel, right, that has another set of numbers, that will generate another output layer, another output, not layer, another output in the same layer, another dimension of that output with a different set of numbers, right? So from this same input image, you have different sets of outputs corresponding to different kernels, right? When you now stack all those kernels together into a three-dimensional cube or cuboid, that is what we call a filter. And the output will also be correspondingly, it will have the same depth as the filter. And in most cases, the size of the output is not determined by the kernel only, but it's determined by the input image, the size of the kernel, the stride, and the padding. So that's some kind of advanced thing, which maybe we can explain that later on. So this is effectively what convolution is. So next time when we say what is convolution, that's what it is. That's at the very basic, the most basic, that's what it is. And this is kind of a another graphical representation of it, where you can see that the here, this is the image, right? This is the kernel, right? And then the kernel is basically taking this image and is mapping it into the next, the next output, the destination, right? And we'll look at all the terminology for this. So key takeaways from convolution: it is a sliding window effectively, but it is a two-dimensional sliding window, right? Not across time, but across space. It's a two-dimensional sliding window that goes from left to right, left to right, left to right. At each stop that it makes, it does a product sum or a sum product element-wise, and the output from it is what goes into the next layer. Okay, I would say, yeah, the next layer, and then it keeps sliding like that until it goes across the entire width of the image and down the entire height of the original image. And you end up having an output that maps to that or corresponds to that. So it is this ability of this kernel to go this, to different parts of the image that way that allows it to detect the local patterns regardless of their position. So if you, for example, had a picture of a cat or an image of a cat, maybe you had a cat somewhere here, right? It can detect it. If you also had the cat somewhere here, it will still detect it because by the time it scans to this point, it will also detect it as a cat, right? That is the principle behind convolutional neural networks. Okay, so we have an animation here, which I'll just let you see. What I just spoke about, that sliding window and the calculation. I don't know if you look at it carefully, right? Okay, this is going through, but you see the numbers, the big numbers are the um essentially the pixel values or activations, right? The small numbers are the parameters, that is the weights in that particular kernel, right? You can see that those numbers don't change, they remain the same. But when you see as it is scanning through, the output here, goes to the corresponding position. And the output is a sum product of this. So you could even pause it and check it out. You can go check more animated animations of this here. There's actually a whole bunch of animations. If you go to this place, you'll see a whole bunch of animations. Right. So yeah, so if you go to animated AI, they have a lot of really nice animations on convolutional neural networks, just on convolution. It really helps to understand. So this is now when you are doing convolution on a three-dimensional cube, right? You now see that each filter is generating a new layer. It's essentially scanning, right? If I pause this, let me see if I can pause this. I don't think I can pause this. But if you look at this, you will see that effectively what's happening is each filter is made up of a stack of kernels, right? I'll come back to this animation. So let me finish explaining everything so that this makes sense to you when you understand. But this is how convolution works, right? We'll come back to that. Okay, so so when you look at this now, this is trying to explain it even more. You now have a kernel, right? This kernel has values. This kernel, for example, is designed to identify or detect edges. And how you will know that it's designed to detect edges, or in those days before neural networks could be trained with backpropagation, people actually used to do convolution kernels hand, crafted. So this is a good example. Handcrafted. Here you will see that it has ones on the left hand side and it has -1 on the right hand side and it has 0 in the middle. So it means that it will have the highest value when there is a color change. So when you take this kernel and you apply it, so there's a few things I want you to see when we talk about padding. The original image, right? The original image is here. This is the original image. You can see that those ones, there are pixel values there. Maybe I can use a different color. The original image, this is the original image. Okay. It has pixel values. Then they they have added these numbers. You can see these are zeros. That is called padding. So when you hear of padding in convolutional neural networks, it is basically fake pixels that you add around the image. So the question is, why do you add padding? We'll talk about that later. But the main reason in this case is that if I were to just use this without padding, I'll be able to move this kernel twice because the kernel size has to be 3 by 3. So because the kernel size has to be 3 by 3, I can only move it 2 steps. The first one, it will be here. And then the second one, it will be here. By the time I have moved it 2 steps, I've gotten to the edge of this image. That is without padding. So I would only be able to generate a new image that is 2 by 2, right? Because I can only make 2 steps at a time. That is where the padding comes in. Now, padding helps me because if I add this padding now, it means that I can now move the kernel. I start from the top here. I can first of all go here, that's 1. Go here, that's 2. Go here, that's 3. And go here, that is 4. So instead of now making a 2 by 2, I can now make a 4 by 4. I can make a 4 by 4, right? I can make a 4 by 4. So the padding helps to increase the dimension of the resulting image in the next layer. So padding is used to control how fast the image gets smaller, right? In subsequent layers. Now you may be asking yourself the question, uh, if the image is getting smaller, am I not losing data? The interesting thing is that as the actual size of the image is getting smaller, the dimension, the the depth can increase. And we are going to see that shortly. That's typically what happens with images. You increase the depth. The depth corresponds to the number of features, right? Um, so in this case now, you can see that I am able to do 4 by 4, like I said, 1, 2, 3, 4, because I've added this padding around the edges. Without this padding, I would not be able to do a 4 by 4, right? I will not be able to do a 4 by 4. I would only be able to do a 2 by 2. So that's the value of padding. Padding gives you some control over the dimensions of the resulting um, image in the next layer. Okay, if not, you would not have much control. You have just images getting smaller or the dimensions getting smaller and smaller. So you can see that if you take this kernel and you do the convolution, for example, let's just take this example here. You have 2 times 1 plus 3 times 0 plus you can basically it is, since everything is 1 and minus 1, it is add everything here, ignore this middle one because this middle one is all zeros, right? This middle one is all zeros, and then subtract this one. So this will be 2 plus 6 plus 2, 8, right? Minus 4, sorry, minus 5. And that will be 3. That's why you're getting 3 here. So you can see how when we apply this particular kernel, the interesting thing you will see is that where there is a change in the color, right, this edge has more negative values, you can see. So this already helps with what we call edge detection. You can tell that this is the edge because this is the end of this place, right? So that's why it has negative values. And another edge, negative values. But in the middle, there's not an edge, you have positive values, and so on and so forth. So these are some of the patterns that were identified by researchers, and they came up with the idea that, oh, okay, yeah, we can use this to detect edges, we can use it to detect corners, and so on. Okay, so now let's talk more about the filters, the concepts rather. So the first concept is the filter. Like I said, the filter is a kernel. So all this while we've been looking at two-dimensional kernels like this, right? But a filter is actually three-dimensional. So you can look at this, right? It now has, this is 3 by 3, but it has a depth. And this depth can have maybe 32. So if you have a layer that has 32 filters, that means it has these 3 by 3 matrices, it has 32 of them, and they are stacked in the third dimension. That's what you are seeing here effectively. So a filter is, that's how I differentiate. For me, I use those terminology, even though you may find that the terminology differs, right? But I choose to use those terminology for easier communication. I use kernel to represent the two-dimensional one, this one, right? So the two-dimensional, that is a kernel, okay? And then I use filter to represent the three-dimension. So when you stack multiple kernels, you get a filter. Okay, that's how I um, identify it for myself. I know that some people may interchange the use of kernel and filter, right? So this is a kernel. When you now stack multiple kernels in the third dimension, right, that becomes a filter. So a 32, yeah, I can add a little bit of thickness here because we're just trying to go 3D, right? So yeah, so this has a bit of thickness, right? So that's just one kernel, and then you stack multiple of them, okay? And it just keeps going that way. And that's this orange thing down here. This orange thing down here is effectively a filter. So the dimension, it goes this way and it goes this way, okay? So this is a filter. So a kernel, you can see a kernel here. Each kernel does one single transformation, right? It basically does a single specific type of feature extraction. And each kernel has, like this kernel has 9 parameters. It has just 9 parameters. These 9 numbers inside here. Those are the 9 parameters that you are using, that you are training, okay? So when you stack 32 of them, that means you have 32 times 9 parameters. This filter will have 32 times 9 parameters. And each kernel in the filter effectively does just one thing. It engineers only one feature. It identifies only one feature and generates a new feature in the next layer, right? Based on what it has learned. Remember, the kernels are the things that are learning. Those are the parameters that are getting updated, in your convolutional neural network. So here we have two kernels, right? This one is -1, -2, -1, 0, 0, 0, 1, 2, 1. So this is kind of an edge detector that will detect a vertical edge. It's going to detect a vertical edge, while this one is going to detect a horizontal edge, because again, you have positive number here, 1, 2, 1, and negative number -1, -2, -1. So by the time you take this filter, sorry, take this kernel and you put in your filter, this kernel is going to identify vertical edges. You stack that filter, you stack another kernel, this kernel, on that filter. So you now have a filter, a kernel. In this filter, you have a kernel that can identify vertical edges, another kernel that can identify horizontal edges, maybe another kernel that can identify, diagonal edges, diagonal left, diagonal top right, and so on, right? You don't know what they are because these are parameters that are learning as you're training them. So they're learning different things. They're learning to identify different things. So you end up with this. And that's what you are seeing here. So whenever you see these three-dimensional representations of convolutional neural networks, one thing you need to understand is that this one here, that's the filter. This is a single kernel in that filter, right? This single kernel is going to transform the image, okay? And it's going to generate a single um, um, output, right? That corresponds to what it has learned to identify. Okay. So filters are small matrices, 3 by 3, 5 by 5, right? They are filled with learnable numbers, like I've said, those are the parameters that we'll learn. Okay. At the beginning, you initialize them with random numbers, just like any other parameter in any neural network. But as you are training the model, the filter begins to learn to detect just one type of pattern. They are specialized. They don't do anything more than that. Each of them is effectively navigating the loss landscape, and they land at one point in the entire loss landscape of images. And they specialize in that one, minimum to identify and detect just one type of pattern. Right. So some of the behaviors like you see here, you can detect a vertical edge, a horizontal edge, a diagonal line, texture block, a lot of things, right? There are so many things a kernel will learn or a filter will learn, right? So when you now stack all of these kernels and you have a filter, then you now have a filter being able to learn multiple patterns. So if you have 32 filters, it's going to produce 32 feature maps, right? So a feature map is a terminology for the output that comes out from a kernel. If you have a single kernel, right, it learns to identify and detect a single type of pattern. It generates an output. That output is a feature map, which is like its new output. So effectively, right, this is the feature map that was generated by this kernel. This is the feature map that was generated by this kernel that is moving in here, right? This here is the feature map that was generated by this kernel looking on this image, okay? So if you have 32 filters, right, um, then you are going to have 32 feature maps. Each map answers a different question about the image. Now, I just said something about a filter being a stack, right? But you can now see that I can take if you can have multiple filters, right? Um, the single output. Oh, by the way, I made the mistake of saying this is a kernel. This is not. This is a single feature map. This is a single output from a single filter. Now, a filter can also be so this filter generates just one output. And this one output is actually the sum of what it does across this entire image. It is all summed into one place. Okay. It is all summed into one place. And then as it is moving, it is creating more elements in the feature map. So this filter creates a single one. You can have another filter that is also three-dimensional that creates another whole layer. Okay. And then another filter that is also three-dimensional creating another layer. That is what this animation was about, which I'm now going to show you this animation. So if you look at this animation, right, what you are seeing here is that you have multiple, let me refresh. You have the first filter, right? This filter scans through this image. This image also has multiple dimensions. It has depth. In fact, think of this as an input, a feature map that is coming in as an input, right? This red filter generates just a single feature map on this output. Now you have another filter that comes in. The brown filter generates another layer in the feature map. Now you have this green filter that comes in and generates another one. Another green filter, slightly different shade of green, and it comes in. This cyan one comes in and generates. So each of these filters will generate a new output, a new layer, essentially a new feature map, a new feature map. And by the time you are done with this 1, 2, 3, 4, 5, 6, 7, 8 filters, right? You have created 8 feature maps. And these 8 feature maps form the entirety of the output that will now carry over to the next layer. In fact, this is effectively the next layer. So what a, a convolutional layer does is what you are seeing in this animation. It takes a three-dimensional input, right? And it applies multiple filters on it to generate another three-dimensional output, where each layer in that three-dimensional output corresponds to the filter. And remember, the filter is detecting multiple different features, and it specializes in detecting multiple features. So it is effectively giving you a new set of features, right? That's why it's called feature map. A new set of features that it has learned to detect. So by the time this is just one layer, by the time you now apply, other layers, you now see that it continues to fine tune the behavior. So there are a bunch of other animations as well, which you can see different things. You see the impact. For example, here you can see there is padding, right? The original image is green, or the original input is green. You now have some padding that changes the dimension of the output. Here there is no padding, so you can see the output is a bit smaller, like we saw. And then you have strides as well. Stride determines the size of the, when it is moving from side to side, how many steps does it skip, and so on and so forth. So that is a visualization of convolution. I always try to do this visualization because it really helps your mental model. Now, when you look at the feature maps, a feature map, like I said, is the output when you apply a single filter. It basically gives you a single two-dimensional flat output. It's another two-dimensional array or matrix of pixels, right? But you see that features are more improved or fine-tuned. These are examples of feature maps, right? You see where bright areas in a feature map typically means that um, that feature is strongly detected by the filter that generated it, right? While dark areas means that that feature is not strongly detected. So if you look at this, for example, you see examples of you know, early layers, right? You see the edges are being detected. So you see an edge here, an edge. This is a diagonal edge. This is almost diagonal, and so on. This diagonal. This is vertical. Sorry, horizontal. Some more diagonal, and almost vertical edges. Then you also see colors and textures where colors change, which is still an edge. Here the edge is from this color to this color, and so on. This is in the early part of the deep neural network, the early layers. Then as you go into deeper layers, you start seeing this kind of stuff where these edges are now combined to give you things that look more like, circles. This could be an eyeball that it has learned to detect this particular, um, you know, um, this particular kernel or this particular swatch, is detecting an eyeball. You see things, basically more structured shapes. You see corners, you see curves, you see lines, you see reflections, you see corners. This is a corner, right? This is like a grid and so on. Then deeper in the network, you now see it begins to actually detect objects, more like objects. You see, this is like a honeycomb, which is a combination of shapes and so on. You see, this looks like a highway or something. You see different things. So the convolutional neural network has started learning more advanced features here, right? These are more advanced features. Of course, this is like if you were looking at the activations, you know, if you're looking at a feature map activations based on specific input, that's how these things are generated. That is not to say that this is actually signal in each of the feature maps. They're actually still numbers, but those numbers have meaning. So the researchers that generate all of these visualizations, there are special methods that are used to generate them. So early feature maps, you see the edges, simple shapes. Deeper feature maps, you see the object parts and the semantic features. Then we have pooling, pooling rather, and spatial reduction. So pooling is downsampling. And the reason why you do downsampling is you want to reduce the spatial dimensions. What's the spatial dimension? It's just the width and height of a feature map. The output that comes from a convolutional layer, that's a feature map. And then the dimension of it, the width and the height, right? That's the spatial dimension. And you want to reduce it because you want to get to a point where the spatial dimension is close to 1, right? Um, so that you can then put it into a fully connected layer for the actual prediction. Okay. So pooling is one of the techniques that you use. And the main essence, like I said, is to reduce the computational load. So remember, we started off this discussion by saying 224 pixel by 224 pixel by 3 if it is RGB. We want to bring it down to being 1 by 1, times maybe 20 features that have been identified, or maybe even 100 or even 1,000, right? 1 by 1 by 1,000 is still much less than the 150,000 we get. So you want to reduce the computational load, also prevent overfitting, because by the time you transform it and put it into a fully connected layer, which is the last tail end of your model, right? You may end up overfitting because you still have too many parameters there. Okay. So what you want to do is still to reduce it. And you want to be able to build robust translation invariant. So translation invariant is wherever in the image that you put this thing, any, particular pattern or whatever it is, dog, cat, it will still be able to identify it. Okay. So pooling will operate on the small regions of a feature map, right? And summarize them into a single value. That's what you do with pooling. And the way you summarize them is basically um, averaging, right? Or choosing the maximum value or choosing the average value. What it does is effectively dimensionality reduction, right? It shrinks the spatial dimensions, right? And it decreases the number of parameters and computations needed. So like we said, translation invariant as well. It makes the model robust to small shifts or rotations or distortions in the input image. So the types of pooling that you do, you have max pooling. So in the max pooling, in that particular swatch or subsection of the feature map that you want to pull, you select the maximum value from that window. Remember, we're doing a sliding window. So you take the largest value. That's max pooling. Okay. So the benefit of max pooling is where you want to highlight the most prominent features in that feature map. You use max pooling. So for example, sharp edges and so on. Average pooling is where you don't take the maximum value, but you take the average value of all the values in that window. So that gives a more smooth and aggregated representation. And then you have global pooling. So in global pooling, you take the entire feature map and you reduce it to a single value. So you typically use this at the end of a network. So this is another animation that is kind of telling you, showing us the whole thing. So you can see in this case, this moving piece, that is a sliding window, that's a kernel. And as it is touching parts of the image, right, it is generating the feature map up here. And you can also see these broken lines is the padding, right? Those are the fake pixels that are added at the ends of each so as to kind of achieve the size that we want to achieve on the output, that is the feature map. So the hyperparameter that you normally would adjust or tweak with convolutional neural network would be kernel size, right? That's the size of this moving window, this sliding window. The stride is how many steps this moving window jumps at is going, from side to side or up to down. Of course, it is obvious that if the stride is more, if it's like now, this one is stride of one, so it's jumping one at a time. But if it moves, if the stride is two, the number of outputs will also reduce. So the stride also affects the size of your outputs, the feature map. Okay. The padding also affects the size of the feature map. Like I've said, the padding is the fake pixels that you put around it, which is normally you give them values of zeros. The number of filters basically is the number of features effectively that you are trying to engineer into the next layer, because next layer is going to be a three-dimensional thing, right? Remember, it's a three-dimensional thing, and each filter is generating a separate feature map. So if you use most right, you are downsampling the image because you are effectively making the image smaller. Um, if you want to maintain the same size, you increase the padding. So the stride and the padding are the two main things you can use to adjust how fast your each layer is getting smaller and smaller. Well, the kernel size also determines how much smaller it is. So there's actually a mathematical simple formula for calculating what the new layer will look like, based on these hyperparameters. So having said that, that's a summary of convolutional neural networks. There are different architectures. The first that started early was the LeNet, which was first tried out or released in 1998. That's one of the first convolutional neural networks. It was designed for a particular kind of um, um, handwriting digit recognition, what we call OCR, optical character recognition. This MNIST is essentially a collection of images of people's handwriting, writing the numbers, the digits from 0 to 9 in different ways, in different shapes, different handwritings, and so on. It is training data that you would use to train a convolutional neural network so that it can recognize whether what is being written is number 0 or 1 or 2 or whatever to 9. So the LeNet was the first that was used for this problem, and it was very successful in it. If you look at the architecture of the LeNet, right, we had just a convolutional. So again, remember we talked about layers. So when you hear of convolutional layer, that's a layer that does a convolution, which we just talked about. The convolution is just this thing that we keep seeing animations of. While the pooling layer, which I'll show later, I've not yet shown an animation of that, but the pooling layer just reduces the size of the feature map of the output, by some factor, the max pooling, the average pooling, and the global pooling. So typically, when you're designing a convolutional neural network, you are just stacking multiple convolutional layers. And then once in a while, you add a pooling layer to reduce the dimension. But there's also this typical rule of thumb. When you add a pooling layer to reduce the dimension, you should also increase the number of filters so that you do not lose information. So that as the layers are getting smaller in the dimension, right, the spatial dimension, as the feature maps are getting smaller, the number of features that are coming out are also increasing so that there's a kind of balance. You don't totally lose out. Otherwise, you will lose information. Okay. So the architecture of the LeNet was a convolutional layer followed by a pooling layer, followed by a second convolutional layer, followed by a pooling layer, and then followed by a FC is a fully connected layer, which is like what we have been doing before. Okay. So the first contribution, the key contribution of the LeNet was that it demonstrated that convolutional neural networks can actually solve, um, you know, all of the problems that, we talk about. So they used it to demo the CNN. Then, some of the limitations of this LeNet, which is like an exemplar of the old design, think one of the main limitations it had was that it was very shallow and it suffered from vanishing gradients. So it was difficult for you to scale and get deeper neural networks from it. You can see that Lenet just had, I think it was just two layers because a pooling layer is normally considered as a layer, right? But you could also count it as four layers, but it had just two convolutional layers, all right? And then, of course, a pooling layer in between, and then the fully connected. So those were the limitations, and the performance began to plateau with depth. But in today's era, you have far more capable deep neural networks, right? Because there's more data to train models. There's more computational capability with GPUs. So you have very deep networks. There are also architectural innovations to stabilize training, to minimize vanishing gradients and so on, right? One of the key innovations is the residual networks, what we call a skip connection. So a skip connection tackles the vanishing gradients problem by turning I'll do some analysis of that later on, but it turns a problem, the thing from a, a product that will vanish to zero, a product of parameters, the gradient, to a sum of gradients, from product of gradients to a sum of gradients. But it helped to solve that. And the skip connection is effectively saying, so let me see if I can sketch it just to help with the understanding. If you are doing a standard, CNN, you will do a CNN layer, for example, then you do a pooling layer. Okay, so let me use a different color for the pooling layer. So I have two CNN layers or two conv layers, and then I'll have two pooling layers, right? That reduce the size or maybe maintain the size. So let's say this is a pooling layer. So I have a pooling layer, and then I have another pooling layer. Okay, then I now have a fully connected layer. So a fully connected layer, I'll also use a slight different color. So you have a fully connected layer here. So that is the stack that you have, and your signal flows this way. Okay, your activations will flow in from the input. It flows into this first conf layer. It goes through the pooling layer. It goes to the next conf layer. It goes through the pooling layer, and it goes to the output layer. Right. That's effectively what is shown here. It's just I decided to draw mine, vertically instead of horizontally, but it's the same thing. You have conf, you have pool, you have conf, you have pool, and you have fully connected. Now, the problem you have is vanishing gradients. As you are training this model, right? The gradients at this early stage, because remember when you're training, you're using back propagation. So your gradients are going backwards, right? So your gradients are going backwards. By the time your gradients get to this early stage, early layers, the value will be very small, going almost to zero. So a skip connection was invented. And the idea of skip connection is take some part of the input signal and add it, right? after every maybe two convolutional layers. That's why Lynette could not go deep because it was always vanishing. It had the vanishing gradient problem. So the way they solved it is, let me show you how they solved it. Skip connection. So what's a skip connection? Now let's take out some of this so it's easier to understand. So a skip connection is something like this. I am now saying I want to I now take some of this input and I sum it. Okay, that was too long. I sum it. I sum it back in here, right? So some part of the original signal is added back, you know, after every two layers, by the way. So remember, the pooling layer is not really counted. I can even take out this pooling layer and say, okay, we'll maintain conv layer. So a ResNet, a residual network, is basically a network where you stack two convolutional layers, okay, together, and then you have a pooling layer, and maybe before the pooling layer. So this is really how it looks like. You take two conv layers, and then before, so you take the two conv layers, and before you get to the output, right? I take a little bit of the input and I add to it. That's that's what um that's what a resonate is effectively. So we still have this going in as usual. We'll still have this coming in. This is a normal pathway for signal through the layers. But I create an alternate pathway where some of the original input, I add it back in to kind of balance it out. Think of it that way, to balance it out so I don't lose all the gradients completely. So gradients will also flow through here, but the gradient that will flow through here, this is summing points here. So the gradient that will flow through here will be just the original gradient. Of course, it's back propagation, so it's going to flow backward this way. But it will be the original gradient with a sum, operation. So what that sum operation does is essentially to stabilize and prevent vanishing gradients. This architecture before the pooling layer is what we call the residual network. And when you hear skip connection, right? This skip connection, this terminology, skip connection, refers to this bypass. You can call it a bypass because it's effectively skipping. But you actually do the skip connection after every two convolutional networks. Okay, so this was as a result of some really, good additional research that was done. And the benefit of the skip connection, right, the residual block, is that it solves the vanishing gradient problem and allows very deep networks. So the skip connection solved what Lynette could only do two layers and it was already having vanishing gradients. But with ResNet and the skip connection, we were able to get very deep neural networks, sometimes 50 layers deep, 150 layers deep, right? And that is where the neural networks really started doing a lot of stuff. By the time you are actually building a neural network that has 150 layers, it's going to take you days, weeks to train it. It's going to take you days and weeks running on a GPU, you know. It's not like what we are doing now where we're just doing basic one or two layers. So here is the mathematical representation of it. The f of x is the function that is going through the layer. So if I want to represent if I want to represent this so that we can see, I always like to kind of correlate the maths. Okay. So the f of x is the function, right? Is the signal going through the block. This block, think of this block as the two convolutional networks that are stacked. So this is f of x here, right? That's f of x. That's the signal coming out from the layer, okay? While x, of course, the skip, is the side stream. Okay, that's the side stream. So that's the value of x because this is x, right? So x just comes in. So that's why the total thing here that you get is going to be this f of x plus x. So effectively, what you're doing is you are taking the signal coming out from this block, which is f of x, and then you're adding it to the original signal. That is residual block. And it was so powerful that one of the key achievements with the residual network was that DeepMind used it to train a neural network that beat um, Lee Sedol in Go. Go is a Chinese game that so far they had up to that time um there had been no AI that could beat human beings in Go, that Go game. Yes, there are AI that beat humans in chess. So that one is an old story, right? Gary Kasparov, Deep Blue, even though it didn't use neural networks, right? It just used some kind of heuristic, right? But that could not be achieved. That same thing could not be achieved for the Go game. But with residual networks, they were able to train a deep neural network. If I can remember, I think it was up to 72. It was just 72 layers deep, right? And they modeled the chessboard after it, and they trained it with human games, human data. After some time, they use that same neural network to start playing its own games against itself. And as it's playing against itself, it is getting better. As it's getting better, that data is being used to train it, and it gets even better and better until it could beat a human being. So that is to show you this was a turnaround, right? Yeah. So when you look at that, you see that you have different architectures now for um, convolutional neural networks. Okay. The that advantage of residual connection, the skip connection, was what made a whole lot of difference. Easier optimization, easier training, more stable training because of the skip connection, because the gradients are more stable. It is now additive rather than multiplicative, right? The network will learn the residual corrections because the residual correction still comes from the input, right? And identity mapping as a fallback. So the new nets that came after the ResNet, right? We have the efficient net. So LeNet, remember the early CNN, it was simple. There was no skip connection, so it could not go deep. So it couldn't learn a lot, or it couldn't do very complex stuff. It could only do the MNIST, which we are going to try out later. Then the ResNet came with the skip connections, and so you could get deeper neural networks. That's where, in fact, it was at the time of ResNet that the word deep learning came into being, because that is when we started we were able to train neural networks to be very deep, or rather to build or architect neural networks that had lots of layers, 100 layers, 150 layers. Then efficient net came with other things, designed for efficiency, compound scaling. So you could scale it depth-wise, add more layers, width-wise, increase, the dimension of each layer, resolution. So it achieves better accuracy with fewer parameters, and it's ideal for limited compute environment. So those are different um, architectures. So we will summarize. In summary, right? These are the key use cases that you use for a convolutional neural network. One, image classification, object detection, medical imaging, satellite imagery, video understanding. And some of the key takeaways is that the CNNs can exploit the spatial structure. In other words, they can, irrespective of where things are, they can identify, they can find it. The filters learn hierarchical features because you have multiple layers. Each filter in each layer will learn a set of features. The next filter in the next layer will learn more complex features. The next filter in the next layer will learn more complex features until the filters at the tail end can learn really advanced features like objects, faces, you know, you know, um, positions and things like that. So the modern CNN solve depth, the problem of depth with efficiency, right? Sorry, problem of depth with skip connection, and then the problem of efficiency with more efficient networks, right? So that is one of the things. That skip connection was a key element. And then we've not talked about transfer learning. We'll talk about that when we come back. But transfer learning makes the CNNs practical for real world task, right? You can take an already trained network. You can even go download in Hugging Face or a couple of these places, download an already trained network and then add, tweak it and train it on your own data and see it begins to do interesting things. We're going to do a bit of hands-on when we come in on Thursday. So the early layers learn feature, the final layers will make the decision. The decision is made by this fully connected layer. So this is basically the summary of how a CNN looks like. You start with an image, right? The image comes in, you have a convolutional layer, you have a ReLU, because remember, at every point there has to be what? An activation function. There has to be that non-linearity. And in CNNs, you typically use ReLU because of the speed of ReLU calculation. And CNNs don't need anything that's more complex as far as activation function is concerned. So you find that most CNNs use ReLU. And then you do the pooling, whether it's a max pooling, average pooling, global pooling, to reduce the size of the feature map so that by the time you get to this fully connected, your plan or your objective is that by the time it gets to the fully connected, the feature map should reduce to about maybe just two pixels, just 2 pixels. So when you flatten it, which is what flatten does, right? Um, it becomes easy to handle. Now, this times 10 times 1000 is telling you that you repeat this. This is just one layer, right? This is one layer. You repeat this layer, you can repeat it 10 times, you can repeat it 1,000 times, any number of times. That is what results in deep learning. That is what results in the marvelous, amazing things that vision models can do, recognizing people and so on. You have to make them really deep, and that's why they are called deep nets. And this whole area is called deep learning. So the key thing is each of these things have their own roles. The convolution detects patterns and learns to detect patterns. The convolution has a filter and everything, edges, textures, and so on. The ReLU introduces nonlinearity, which we've talked about before. The pooling reduces the size of the feature map while keeping the important features, so you don't lose the important features. The pooling reduces size so that by the time you do this 10 times, 100 times, right, or even 1,000 times, you now end up with a layer that has maybe a 2 by 2 or a 1 by 1 feature map. Then you flatten it. So what flatten in this case means is, let's assume you have trained your model here. So effectively, you end up with something that is like, I don't know if I can rotate this, but you end up with something like this. Let me use lines. So you end up with a feature map that is basically maybe 1 by 1 or 2 by 2, right? So if you end up with a feature map that is 2 by 2, but it is very long because in the process of being trained, more and more features are added. So each of these additional dimensions corresponds to additional features. So if you look at this, let's assume we had trained this and it somehow is able to get maybe, let's say, up to a depth of 512, right? Filters. So this is 2 by 2, right? But it now has a depth of 512. Okay, 2 by 2 by 512. So you're going to flatten this 2 by 2 into a single vector of the size of that single vector will be 2, right, by 2 by 512. That will be the size of the vector because effectively you are taking this this 2 by 2 feature map here and you flatten it out into a single this thing. So you end up with a 2048 basically, which is um that will be the number of elements in that vector. So this 2048, that's what flatten does. Okay, so when you hear flatten basically takes a 2 by 2 by 512 and converts it into an input of 2048. So that this your fully connected layer. Let's assume you want to do a classification. You want to just produce a single prediction of yes or no. Yes, it is a cat, or no, it is not a cat. Then this your fully connected layer will now have 2048 inputs, right? And it will have just one output. So the number of parameters in it will be 2048, which is not going to be too much. But imagine if you had this image and this image was 224 by 224, right? That would be 150 something thousand like we saw at the beginning of this. So you end up with a fully connected of 150 something thousand, no, 150 something million parameters. That's what this fully connected would have been if we did not put this stack of convolutional um, layers before it. But the convolutional layers allow this feature engineering and reduction of the size until it becomes this 2 by 2 by 512, which we can then stretch out to a 2048, right? So we now have 2048 by 1, which is the parameter size just 2048, but we did not lose quality, right? We did not lose anything. And this fully connected is now what does the actual prediction. It learns the representation, right? And produces the prediction. This is the principle behind the convolutional neural networks. So I think I'll pause it here. When we come next, we are going to do, there are 3 different, traditional um, examples that you would do. I'm going to share this MNIST with everyone, and I would like everyone to try it on your own and share with me your Jupyter notebook, right? Um, It's the MNIST is a handwritten digit data set that contains images of handwritten digits, 70,000 samples. They are grayscale. That means they're not color. So the size of the pixels are 28 by 28. Because it's grayscale, it's just one layer. It's not 4 layers or 3 layers. So it's 28 by 28 by 1. You have to use Lenet first to classify this and see how well it does. You look at the metrics, the different metrics, accuracy and precision recall and all of that. Then you also do the same thing with using a ResNet. Maybe you can stack 10 ResNets, use a GPU. This is when you start talking about GPU and see the accuracy using a ResNet with 10 layers versus a Lenet that had just 2 layers. You will see the difference in terms of the performance. And then Cypher is this one, is still data, but it has 10 classes. This one has dogs and cats and other animals, and it is colored. So we could also try that. And then ImageNet is a much more larger set of images. But again, you you do. So I'm going to post the examples I would like everyone to go and do. Just get your hands dirty and get used to training. This is now real machine learning training, right? It's not sklearn. It's really about tweaking your hyperparameters and getting that accuracy. So you will do MNIST with a Lenet architecture, then you do MNIST with a ResNet architecture of, let's just say, 10 layers. Okay, Lenet is 2 layers, ResNet is 10 layers, and then we see. Then show me your evaluation values: accuracy, recall, precision, F1, and so on. So that's it. I hope this class was helpful. This is a highly theoretical class, right? But I always prefer that we focus on understanding the ideas behind these things. Writing the code is not hard. Writing the code is 5 lines of code with PyTorch. There's already a conv2d. I can even give you examples that you can use, right? So writing the code is not hard. But when you understand the concepts, right, it becomes so much easier when you understand the concept to think about it. You can design your own neural network because you understand the principles behind it. That is what machine learning core is all about. It's not really about writing code. It's about understanding so that you can make your own designs. So I'll end it there. Any questions?